Hello my dear students. Today we are in lecture number 56. It is lecture number 56 of chapter 4, moving charge and magnetism. Student, we have now maximum 2 to 3 lecture in this chapter. We are about to conclude this chapter. Today we'll study about the Ampere circuital law, student. In last class we have studied the magnetic field due to solenoid, and it was very complex calculation. Today we'll see how this Ampere circuital law make this calculation so much easy for us. Alright my dear student. So here the Ampere circuital law, the topic of today. Ampere circuital law. My dear student, actually Ampere circuital law, it really works as to simplify the calculation as done by Gauss law. I hope you remember the Gauss law simplify the things to find the electric field. In same way, here Ampere circuital law will simplify all the things to find magnetic field. All right. Actually, we use this Ampere circuital law to find magnetic field due to current loop. Okay, everywhere the current loop, my dear student. Now, here the first thing we do know, it is Imperium loop, as we have studied the Gaussian surface. In same way, Imperium loop. What is this Imperium loop, my dear student? Remember, the Imperium loop is an imaginary circuit or the loop that will enclose the current element entirely. All right. Now we are going to here make a simple example. Suppose this is my current carrying element. All right, and I have to find the magnetic field at this point P. So you have to make the radius from this conductor, and of this radius you have to make a closed loop, and this will be considered as the Imperium loop. All right, this is the Imperium loop. You need to find the magnetic field over this Imperium loop only. All right, so there should be some important point about the Imperium loop. You should write in your notebook, the one by one. The first you should write, it encloses the conductor in 2D shape. This one is the 2D. Remember, this is not the 3-dimensional. It encloses the current conductor or the current element in 2-dimensional shape. The second point you can write, magnetic field must be considered on Imperium loop. Okay, you have made the Imperium loop of radius r like this way, and you are going to calculate the magnetic field over here only. All right, so the magnetic field must be calculated over the Imperium loop. Next point you can write, the magnetic field will be along the tangent to the Imperium loop. If you find the magnetic field over here due to this conductor, of course, if the current is moving up, the magnetic field will be upward. It means the tangent to the Imperium loop. It is circle, then the tangent, if it is the circular, then the tangent direction will give you the direction of magnetic field. So the magnetic field will be along the tangent to the Imperium loop. All right. And one thing, and the last thing, which is very important, if you are going to apply here the Ampere circuital law, then current must be steady. This is the very important terms and condition for applying Ampere circuital law. All right. In short, we used to say it is ACL, Ampere circuital law. All right. ACL. Ampere circuital law, my dear students. Okay, so the current should be constant, that is the steady, it is not fluctuating. Well, with study we will see that Ampere circuital law, it works somewhere where the current also changes, but there's some certain conditions. Now you should write the statement of this was the Imperium loop, the concept of Imperium loop. Now the Ampere circuital law, write the statement, my dear student. Statement of this Ampere circuital law, that is the ACL. Kindly write down the line integral of magnetic field. The line integral of, you should write, my dear student, the line integral of magnetic field. Line integral means the B dot dl of magnetic field. The line integral of magnetic field must be equals the mu naught times the enclosed current. Mu naught times the enclosed current. This is the I enclosed, En, enclosed current within the Imperium loop. Within the Imperium loop. And this is the equation for Ampere circuital law that we will use. All right, my dear friend? Yes. And the same Ampere circuital law for you are going to apply for n turns, okay? For n turns, then you will write the B dot dl, both are the vector quantity. This is the closed integral. B dot dl is equals to n times mu naught I enclosed. Okay, that's it. This is for the n turns. So you will write Ampere circuital law in this way. Okay, my dear student. Now we are going to apply here the Ampere circuital law and to write the one or two application. We'll see the three application. I think you have to study. Now remember, B dot dl is equals to mu naught I enclosed. Here you can see if this is the current carrying conductor, current is flowing I, all right, and this is the elemental length. Sorry, that's not the dl actually. The current is flowing, it is I. Okay, you have to find the magnetic field at this point P. So of this radius you have to make Imperium loop that we have studied. Now try to find out the I enclosed and here I enclosed and dl in this diagram. I enclosed is this one, that this Imperium loop encloses the total current. Now the dl actually we have to use at the Imperium loop. This one is the dl, the small length. Okay, the small length along the Imperium loop. You can take the dl over here also. Okay, so this is the dl. If you will integrate this dl for entire value, what will be the value? If you will integrate this dl, what will be the value over here? Then you will find if radius is r, then dl will be integrated to the whole value. It is the 2 pi r. Okay, so remember, this is the dl. Now we have studied here the Ampere circuital law. We are going to apply and we'll see some application. Okay, so give the heading now, application of Ampere circuital law, that is the ACL. Okay, the first application will try to find out the magnetic field due to the straight conductor. Okay, magnetic field due to straight conductor. Okay, all right, so this is current carrying conductor. Suppose this is straight conductor Alright, the current is flowing I. We have to find magnetic field at this point P. What we have to do now, we have to use this as radius and make a Imperium loop. So let me draw here an Imperium loop. Yes, this is a Imperium loop. Alright, current is flowing in this way. Now applying, remember here what are the values we have given. Here the I is the current. Alright, R is the position of observation length. Now applying ACL, we can write B dot DL as mu naught I enclosed. And what is the enclosed current? Try to find out the enclosed current. It is the total current enclosed by this Imperium loop, so this will be the I. Now B we have to find, take it out, DL, it is equals to mu naught I. Now DL, actually DL is nothing but the length on this Imperium loop, and this is the DL. So what will be the value of entire integral of this one? It is the 2 pi r. So we will find the magnetic field. Let me write over here, and it is B dot DL, and DL it is the 2 pi r. It is equals to mu naught I. So B is equals to mu naught I by 2 pi r, and this was the magnetic field. Try to recall, we have calculated for the straight conductor. Am I right, my dear student? Yes, this was the magnetic field due to the straight conductor, mu naught I by 2 pi r. So in this way we have calculated. Now the next application, it is the next one. Let me wrap this one. This was not very difficult, my dear student. Now the next, it is the magnetic field due to solenoid. The second one, the second application, we have magnetic field due to solenoid. All right, yes, okay. So first we'll draw here the diagram of solenoid. And we have studied already about this solenoid. This is the non-conducting porous material over which we are winding here a conducting wire using some source. We are supplying here the current. The current moves in same fashion in all conductor. Here this is the axis of solenoid. We don't need to waste much time, my dear student, over this one, because we have studied in very detail, all right, about this one. Okay, now let me take here the Imperium loop. I'm taking this Imperium loop by the red marker, this one. I've chosen here the Imperium loop of this length because the solenoid is of infinite length. Okay, I've been chosen here. Suppose my Imperium loop having the name A, it is B, C, D. Now here for the entire loop, that is the Imperium loop, you can see the current is, of course, it will be fine somewhere, but since the Ampere's circuital law, it was B dot dl as the vector quantity. B dot dl. So the angle is also very important to be considered. It was the mu naught I enclosed. Here the B dot dl, it is the B dl cos theta. Alright, and the mu naught I enclose. This will be. Now, my dear students, look at here. We are having the fourth section of this Imperium loop here, A, B, C, D. So, when we will apply here the A for the Ampere circuital law, it is Imperium loop. For AB, we'll have B dot dl for AB for A to B plus B dot dl for BC plus B dot dl for CD plus B dot dl for DA, and it is equals to mu naught I enclose will find. Okay, now look at here, B dot dl for AB. All right, for AB, the direction of magnetic field and the L. What will be the direction of magnetic field for solenoid? We know that the magnetic field, it is, if the current is moving in this way, so the magnetic field will be in this direction. We know very well. Okay, in this direction. This is the direction of magnetic field. Before finding the magnitude of magnetic field, we are having the direction of magnetic field direct. Okay, so we are applying this one. From A to B, the direction of magnetic field either along the direction of this AB, that is the DL, or opposite to the DL. The theta will be either 0 degree or 180 degree. Okay, so it's okay that B dot dl and the length, suppose this length of Ampere circuital Imperium loop, it is L. Suppose it is L, and only this small elemental Imperium loop we are considering, and our conductor having, that solenoid having this much length only. All right, okay, so we'll write here the B dot dl, so it is L plus, for this one, B dot dl for BC. You can see the dl will be in upward direction and the magnetic field will be either in this direction, so the angle will be 90 degree, and cos 90, it will be how much? It is 0, so this will be the 0, plus B dot dl for CD. This CD is out of the magnetic field. Here the current will not enclose, the magnetic field is not present, so this already 0, plus now this DL, this DA, again this DA is perpendicular to the magnetic field, so the theta will be 90 degree and this will be the 0. Now the mu naught times current, how much the total current was enclosed within this loop? It is I. Okay, but remember students, if one loop it was moving through this Imperium loop, then the current can be written the I, and we'll apply the Ampere circuital law at the mu, that is the mu naught, okay, I enclose. But here the number of turns are given, n number of turns it is moving, so we'll write mu naught I n, okay, for the n turns. In bracket you can write for n turns. All right, so here the B dot dl, it is the BL is equals to mu naught n I finally, and the B can be written as mu naught n I by L, and this n by L, we know that it is the small n I. Okay, so this is the magnetic field due to solenoid. All right, so you can see, my dear students, this calculation is very much easier than that calculation we use to find the magnetic field due to solenoid using the integration and all the mathematical stuffs. Okay, now let me write this. This is the magnetic field due to solenoid, my dear student. Now we'll find the magnetic field due to straight conductor inside, outside, and at the surface of conductor if the conductor is very thick. Okay, we have studied if the conductor is one dimensional, then the magnetic field at any point which is at distance r, the magnetic field will be mu naught I by 2 pi r. But suppose if this one is the conductor and we are going to find out the magnetic field inside the conductor at certain point. Okay, magnetic field inside the conductor at certain point, like this way. First, we'll give the heading. It is the magnetic field due to a straight thick wire. Magnetic field due to thick wire. All right. Now, this is a conductor. Look at here. This I'm having the conductor. This is the very much thick, and this is the axis. All right, my dear, this is the conductor actually of this particular thickness. I'm representing. I'm drawing the conductor over here. All right, this one, and the current, it is total current flowing through this conductor. It is I. The total current. This is not the conductor, remember, this is the axis of the conductor. This one is the conductor actually. Okay, and the current is flowing how much? It is I. The radius of the conductor, it is given r. This is the radius, okay, of the conductor. It is r. Now suppose if we want to find the magnetic field at this point, if we wish to find the magnetic field at this point, if we wish to find the magnetic field inside the conductor at this point, okay, then how? If we wish to find magnetic field outside the conductor, suppose this is the observation length x. Here in first case, this x is greater than r. Remember, where the current is flowing? Current is flowing through this conductor only. All right. So let me first make the Imperium loop. All right. Yes, this is the Imperium loop. Now this Imperium loop encloses, and this will be the DL. All right, this is the DL. My dear student, you can see this Imperium loop that is marked by the red. It has been enclosed the total current flowing through this conductor. All right, so we can write here for this first case as point P1. Suppose this is the point P1. Okay, outside the conductor, case 1. We'll study all the cases. Case 1, x is greater than r outside the conductor. All right, what will be the enclosed current? Here the I enclosed, it is I only. All right, applying Ampere's circuital law, what we can write? B dot dl is equals to mu naught enclosed current, it is the I only. All right, now B out dl is equals to mu naught I, and B times the dl, the value of dl, it is the 2 pi x. 2 pi x mu naught I. So B is equals to mu naught I by 2 pi x. All right, outside the conductor, you can see if this mu naught is constant, I is constant, 2 pi is constant, it means this B is inversely proportional to x. Yes, outside the conductor, sorry, inversely proportional to x. As you will go away from the conductor, you will find the magnetic field decreasing. All right, yes, case 2. When x is equals to r, okay, at the conductor surface. At the conductor surface, my dear student, you have to make the Imperium loop, and it is approx equal to the radius r. All right, so nothing much you have to change. Remember, the current will be enclosed here. The I enclosed will be total current. the total current, and the radius, it is the Ampere loop. The radius will be x is equals to r, and nothing is going to be changed, so the same equation will be considered. Only it is the mu naught I divided by 2 pi x will be r, nothing else. Now you can see this r is not going to be changed, the conductor length is not going to change, so the mu naught I 2 pi r, this is all constant, and this is the, I think, value of the magnetic field, and it is the constant which is the maximum, I think. Okay, now case 3, all right, this x is less than r inside the conductor at P3. Okay, it was the P1 and this was the P2, this was the P2, now this is P3. All right, this is P3, where P2 and this is the P3. So you will form here an Imperium loop. You will find this much is the Imperium loop, my dear student. Now you know that uniformly the current is flowing through this conductor, and this Imperium loop encloses only this much area. It means you will have now the conductor portion only this one, and this one the current enclosed. Okay, here only this much the current enclosed. So our first duty is to find how much current flowing through this red conductor, all right, which has a radius x which is less than r. So we go for this one. Here let me find out the current first. Since the current is uniform flowing, okay, the current is uniform. Now through this area pi r square, okay, through this area pi r square, the total current was flowing this one I. So from this area we have to find pi x square. Pi x square, how much current will be there? Pi r square times pi x square, and suppose this current as I dash, I enclose at I dash. Okay, this current is as I dash through this conductor I dash. So what will the value of I dash? It is I times this pi will be cancelled out, so the x square over r square. Now this is the new enclosed current, and this is the I enclosed for third case. Now applying Ampere circuital law, B dot dl equals to mu naught I enclosed, it is the I dash. All right, could we write? Yes, we can write. Here the B into dl, and the dl, it is how much? It is now 2 pi x. Yes, 2 pi x is equals to mu naught, and the I enclosed we are having here the I times x square over r square. So B can be written as this one, mu naught I x square over r square times 2 pi x. What is the result? Here the x will be cancelled out, so mu naught I x by 2 pi r square. Now you can see, my dear students, the magnetic field, it is mu naught I 2 pi r square. It is the constant. It means the magnetic field is now, this is magnetic field for the point 3p3. Here the magnetic field is directly proportional to x. All right, as you will go away, that is the x increasing, as you will go away from the center, x will increase. So as you are going away, the x is increasing, the magnetic field is increasing, and here the magnetic field will be maximum. As you will go out, the magnetic field will be decrease. All right, the magnetic field will be decrease. Remember, now you need to draw the graph. This will be asked in your board examination, to draw the graph for magnetic field with the as a function of this x. All right, my dear friend. So you have to explain this graph. Now let me draw the graph. here the parameter I'm using. You can see, my dear student, this is the R. So let me write here the value. This is the R, okay, and this is the X. This one is the X. Yes, this is the X. On this axis, X will be considered in meter, and this will give you the magnetic field in upward direction in Tesla. You can write. Now, what will the magnetic field over here? As the X will be 0, the magnetic field will be exactly, yes, it is 0. As you will go away, how the magnetic field increases? B directly proportional to X, and the graph for the B directly proportional to X, it will be the straight line like this way. Here the magnetic field at the R, it is constant, and how much the magnetic field it is? Yes, we have calculated the magnetic field mu naught I by 2 pi R. Here the mu naught I by 2 pi R, so put the maximum value. Then after, how the magnetic field changes? How the magnetic field changes? So you have consider for outside, it was the relation B inversely proportional to X. Try to remember. Yes, try to recall. It is B inversely proportional to 1 by X. So this will decrease like this way. All right. So this is directly proportional to R, and this is inversely proportional to X. This is directly proportional to X, and this is inversely proportional to X. At this is for point P3. This is P2, and this is for point P1. All right. So this is your required graph. You will be asked in examination. Okay, my dear student. Now you're having one more topic, and it is the toroid. Okay, toroidal solenoid. Actually, you need to find the magnetic field due to toroid. Okay. So today we will study how this toroid form, and in next class we will derive the mathematical equation of the toroid. Okay, so let me wrap this one, my dear student. Remember, the toroid is endless solenoid. This is also considered the endless solenoid. Okay, the toroid is also considered the endless solenoid. Okay, and how we form the toroid? Actually, if you will bend, suppose this is the flexible cylindrical, okay, material, and you winded wires over this one, all right, for the n turns, and then after you make this one as a circular loop, and you connect this, both the end, this end and this end, to each other, coalesces. Okay, so you will find such this type of arrangement. You'll find this type of arrangement. Okay, and there is turning in this arrangement. You can see it is like this way. Okay, in next lecture, my dear student, I will try to start the class as I have to just find the derivation. The current is in entering, okay, and it is leaving. So this is your toroid. Toroid, kindly write down, my dear student, the circular arrangement of solenoid. Okay, it is the circular arrangement of solenoid in such a way that the two ends of solenoid, that is north pole and south pole, as we know that the solenoid behaves like a short bar magnet. So the north pole and south pole are coalesces to each other to make this as endless. All right. So this is considered as the toroid, where the magnetic field actually exists inside the toroid. So this is the space where we got the magnetic field for the toroid. This is the space we got the magnetic field inside the toroid. All right, there is no magnetic field in this space. Okay, there is no magnetic field outside the space of the toroid, and this particular arrangement is considered the toroid. Okay, in next class, my dear students, we'll derive the equation for the magnetic field outside, inside, and at the surface of this toroid. Even you can also derive by yourself if you understand how to apply the Ampere circuital law for the solenoid. This is also very this will be the very easy for you, okay, to derive the equation. So in next class, my dear students, we will derive the magnetic field due to this toroid, and then we will start that very important topic. It is moving coil galvanometer. Okay, my dear students. So this is all about today's lecture. Thank you, my dear students.